Hello and welcome to the video solutions here for this A-level maths mock exam paper. Now as you can see then, this is Set C paper 2, but for many of you, you'll be using this as a predicted paper for the upcoming 2025 A-level maths exam series. And that's absolutely fine, right? Just as a quick kind of note here, many of you have been asking, we do also have Set A and Set B. You can view the video solutions over on our YouTube channel, AJMaths, or if you want to view the paper as well, you can view that on our website, ajmaths.co.uk, alongside worksheets and also revision videos. So go and check that out if you are looking for a little bit of extra revision in the run-up to your upcoming A-level maths exams. So before we jump into the paper here today, just a few quick notes to make them. So again, this practice paper closely follows the Pearson Edexcel specification for A-level maths. However, Pearson Edexcel have no affiliation to this paper and are not responsible for any of the material featured in this paper. Again, all this kind of good stuff and standard stuff that you should be used to. You can use the form of the book, you can use the calculator, and again, you get 2 hours as you would with any standard A-level maths exam. And as we saw with paper 1, there are also 14 questions in this paper as well. Other than that though, I don't think I really have anything else to say here. So again, if you want to have a go at Set A and Set B, you can view those over on our website, ajmaths.co.uk. But other than that, I'm just kind of rambling here. So as always, best of luck with your upcoming A-level maths exams. So let's not waste any more time then, and let's just get started with question 1. So let's just make a start here then with question 1. And as you would expect with question 1 here, quite a nice easy question just to get us started. So for this question here then, what we're given is the point A, which has coordinates of 4, -3, and the point A then lies on the curve with this equation here. So all we want to do then is find the point to which A is mapped when the curve with this equation here is transformed to the curve with the following equations. Now for part A then, what we've got here is y is equal to f of x plus 3. Okay, now this here then is simply a horizontal translation. This here is a translation by -3, 0. And in that case then, all we need to do here is just simply subtract 3 from the x coordinate here. So in that case then, what we get here is 1 minus 3. As you can see then, nice and easy, right? Now for the next part of this question, part B again, nice and straightforward really. What we've got here then is y is equal to the modulus of f of x. So y equals the modulus of f of x here. So because we're taking the modulus then of the full function here, what that means then is all y are positive. And in that case then, what we obtain here is simply 4, 3. Again, nice and easy, right? And then to finish with here, the very last part of question 1 then, part C, I've got y is equal to 2f of x minus 1 plus 3. So y is equal to 2f of x minus 1 plus 3. Now, this part of the question is really the only part that could cause an issue. And the reason for that is because we do need to be careful here in the order in which we apply these transformations. Okay, so what I need to do here is start by applying the horizontal translation. We then apply the stretch here, that's this 2 on the outside. And then finally to finish with here, we apply the vertical translation. So let's just go through this step by step, right? So we start by applying the horizontal translation here. Because it's x minus 1, we simply add 1 to the x coordinate here. So in that case, then I get 5 minus 3. I'll do that underneath here just so you can kind of see that it's scrap working rather than a solution. So we get 5 minus 3. We then apply the stretch here, that's this 2 on the outside. So this 2 here, what that does then, it just times the y coordinates by 2, right? That's how we apply this stretch. So I get 5 minus 6, like so. And then finally here, we apply the vertical translation. So because it's plus 3, we simply add 3 to the y coordinate here. In that case then, to finish with here, what we obtain is 5 minus 3. Okay, and again, to be honest, for question 1, I shouldn't really be causing any issues, but hopefully nice and straightforward, right? So there we have it then. That gives us the solution to question 1. So moving on to the next question here then, let's just have a go at question 2. So starting off with part A then, where all we want to do here is express 7 sin x minus 24 cos x in this form here, where r is strictly greater than 0, and alpha is between 0 and pi over 2. We need to give the exact value of r, and also give the value of alpha in radians to 4 significant figures. So for part A then, pretty standard stuff here. This is just simply the harmonic identities, or the R formulae, right? Whichever you know this as. So let's just start here then by writing this down and setting that identical to r sine of x minus alpha. We've got 7 sine x minus 24 cos x is identical to, it's r sine of x minus alpha. Okay. Now, if you want to here, you can use the compound angle formula for sine of x minus alpha, equate coefficients, and go about it in that way. I do think that's unnecessary here for this question. This is a pretty straightforward application of the harmonic identities, right? So to get us started here then, let's evaluate r. Now don't forget then that r here, to evaluate r, is simply an application of Pythagoras. Straightforward stuff, right? From GCSE maths. So this here then is the square root of, so it's 7 squared plus minus 24 squared. So 7 squared plus minus 24 squared. Okay. If we evaluate this here then, what do we get? So 7 squared plus 24 squared, because obviously minus 24 squared is just the same as 24 squared. That gives us the square root then of 625, which is simply 25 there. Bosh, nice and easy. We now also need the value of alpha here in radians to 4 SF. So in this case here, tan alpha would simply be 24 over 7. So tan alpha is equal to 24 over 7. And in that case then, if we want alpha here, that is simply tan inverse or arctan, whichever you prefer, right, of 24 over 7. Wash this into your calculator here. What do we get then? So I get 1.287. Obviously, just ensure that you're working in radians here, right? If we want the value of alpha in radians, then obviously your calculator needs to be in radians. So what you should get here then, to 4 significant figures, is 1.287. And then to finish with here, just rewrite this in this form here, just replacing r and alpha with what we've evaluated. So in that case then, what I get here, or 7 sine x minus 24 cos x is, so this is identical to, so r sine of x minus alpha, so r is 25, get 25 sine of x minus alpha, where alpha is 1.287. 1.287 there. Okay. And there we have it then. So hopefully quite a straightforward application there of the harmonic identities for part A. So as we can see then, for the next part of this question here, part B, we're given this function here, f of x, and then we want to find the following two things here. So for B part 1, what do we want to find here? So we want to find the minimum value of f of x here, where f of x is given as follows. Now, if we want to find the minimum value here of f of x, then basically what we need to do here is make our denominator as large as possible. Now, I'm looking at this function here and thinking, is there any way that I can link that to part A, right? And what I noticed then is 21 sine x minus 72 cos x looks very, very, familiar or similar to this expression here in part A. Now, in fact, it's actually 3 lots of this expression here in part A, right? 7 times 3 is 21, minus 24 times 3 is minus 72. So, in that case then, what is the maximum value of this expression here? Well, that is when sine of x minus alpha, which in this case here is sine of x minus 1.287, is equal to 1. So it's 25 times 1. So the maximum value here of 7 sine x minus 24 cos x is 25. Let's just make a note here. So max value is 25. So if this here is 3 lots of this expression here in part A, then the maximum of this here is 3 lots of the maximum value of this expression here, right? That should seem hopefully quite intuitive and obvious. So what I've got here then for f of x is, so we've got 20 all over them. I've got 5 plus 3 lots of 25. Let's just simplify this here. I've got 20 all over then, 5 plus 75, giving us 80, and 20 over 80 is just simply 1 over 4 there. Okay, so there we have it then. That gives us the solution to B part 1. And then for the second part here of part B, we want to find the smallest value of x for which this minimum value occurs. Now, we've already mentioned that, right? So this occurs then. So this occurs when sine of x minus then alpha, which in this case is 1.287, 1.287 is equal to 1. Okay, so if we want the smallest value of x here for which this minimum value occurs, all we need to do here then is just solve for x, right? So start by taking sine inverse of both sides. Should hopefully be quite a straightforward trig equation here. So again, just take sine inverse of both sides. In that case, then what I get here is x minus 1.287 is equal to sine inverse of 1. Now don't forget then we are working in radians here, so sine inverse of 1 is pi over 2. Get pi over 2 there. And then finally to finish with here, let's add 1.287 to both sides here. To finish with then, the smallest value of x for which this minimum value occurs is pi over 2 plus 1.287, which gives us 2.86 there. Okay, and there we have it then. So hopefully, nothing too challenging there really for question 2. Again, as we mentioned at the beginning of the question, it's just a simple application of the harmonic identities. Okay, so there we have it then. That gives us the solution here to question 2. So moving on to the next question here, then question 3, as we can see, right, we have a question on the factor theorem. So starting off with part A then, where it says prove that if x minus p is a factor of f of x, then f of p is equal to 0. So to get us started here, we have a proof type question. Now, if x minus p is a factor of f of x, and what we can do here is write f of x in the following form. So f of x here then is equal to x minus p, because x minus p is a factor of f of x, times by g of x here, where g of x then is just some polynomial. Okay? Now what I want to consider here then is f of p. So f of p here. So all we need to do here then is just replace any x's with p. We get p minus p times by g of p. And hopefully you can see what's going to happen here. So p minus p is just 0, right? So therefore, f of p is equal to 0 times by g of p. But of course, anything times by 0 here is just 0, right? And in that case, then f of p here is equal to 0, exactly as we require. So as required there we have it, proof complete. So there we go. That gives us the solution to part A. Now for the next part of this question here, then part B, as we can see, then we're given f of x here, where f of x is a cubic polynomial. So the a and d are constants, and we're also given here that 3x plus 1 is a factor of f of x. So for part B then, we want to show the following. Now, if 3x plus 1 is a factor of f of x, then in that case here, what that tells us is f of minus 1 over 3 is equal to 0. Okay, so all we need to do here then is just substitute minus 1 over 3 into f of x here, right? Set that equal to 0, and hopefully we should obtain this expression here. So what I've got here then is, so I've got a times minus 1 over 3 cubed. So a times minus 1 over 3 cubed. I've got minus a times minus 1 over 3 squared. So minus a times minus 1 over 3 squared. We've got 3 lots of minus 1 over 3. So 3 lots of minus 1 over 3. And then finally here, plus d, right? And we know then, by the factor theorem here, that all of this is equal to 0. Okay? So let's just simplify here and clean this up. So what do we get then? To get minus 1 over 27 times by a. It's minus 1 over 27a there. Minus 1 over 3 squared is 1 over 9. So times that by minus 8. I get minus 8 over 9. 3 times minus 1 over 3 is just minus 1 plus d then. And this here is equal to 0. Now, as we can see then, the coefficient here for a is just minus 1. So it would seem here that if we times through by 27, that would be pretty sensible, right? We should hopefully start to get towards this desired result. So timesing through then by 27 here, what do we get? I get minus a. I've got minus 8 over 9, so if I times that by 27, I get minus 24. Minus 1 times 27 is minus 27. And then d times 27 gives us 27d. And all of this here is equal to 0, right? So minus 24 minus 27 is minus 51. Take that over to the other side. And then what I've got here on the left-hand side is 27d minus a. So therefore then, 27d minus a is equal to 51 as required there. Okay. Good stuff. So that gives us the solution to part B. And then finally for the very last part of this question here, part C, we're also given that x minus 1 is also a factor of f of x. So what we want to do here then is find the value of a and d. So if x minus 1 is a factor, then in that case here, what we know is f of 1 is equal to 0, right? So all we need to do here then is just substitute 1 into f of x, okay? And what should happen then is we should obtain another expression similar to this, right? So in terms of a and d, what we obtained here then is simultaneous equation, which we can go on to solve, okay? So f of 1 then, what do I get here? So 1 cubed is just 1, so I get a. Minus 8 times 1 squared is minus 8. Plus 3 lots of 1, so plus 3. Plus d then is equal to 0. So what I can do here then is clean up the left-hand side. So minus 8 plus 3 is minus 5. Take the minus 5 over to the other side. I've got a plus d is equal to a 5. And at this point here then, what we now need to do is just solve. So we need to solve them. A plus d is equal to 5. And also 27d minus a is equal to 51, right? We want to solve these simultaneous equations here. So what I'm going to do here then is substitute a here into the second equation here. I get 27d minus a then. So a here is 5 minus d. So minus then 5 minus d is equal to 51. So what do we get here? So I get 27d minus 5 plus d is equal to 51. So add 5 to both sides, and 27d plus d is obviously 28d. 28d here is equal to 56. Divide both sides by 28, right? And in that case, then d is equal to 2. And now that we have the value of d right, we can easily find the value of a. So a is equal to 5 minus d. Put that over here. So a is equal to 5 minus d. So therefore a is equal to 3. Okay. So if I just give the actual solution here, we'll do it in red then, so it's clear. So therefore A is equal to 3, and D here is equal to 2. Okay, so this here then, I'm putting kind of like the bubble or cloud around, whatever you want to call this. This here is what you should get for A and D there. Okay, so there we have it then. That gives us the solution here to question 3. So for the next question here, question 4, we have a question on circles. So what I'm given here then is the points P and Q which have the following coordinates respectively. We're then given that PQ is a diameter of the circle C, and then for the first part of this question here, part A, what we want to do then is find an equation of the circle C. So for part A then, where do we begin here? Well, what I've got then is 2 points here that are the endpoints of my diameter, right? So we have a quick sketch here. Like I said, it's a very quick sketch. It doesn't need to be perfect. That's my x-axis. This here is my y-axis. I've got 4, 1. Let's say that's there. And I've also got -6, -1. Let's just say that that's there, for example, right? That's P, and that is Q. Okay. So these 2 points here are the endpoints of my diameter, right, for the circle C. So if I join these up then, we get something like that. This is clearly going to give me my circle. It's not going to be perfect because I'm not Picasso, but we'll get something like that, right? So if I kind of join that up then, we'll get something like this. It's not great, but honestly, it really doesn't matter. So what I've got here then is P and Q, okay? So hopefully it's kind of obvious here that the midpoint then would give me the center of the circle here, which I'm going to say is kind of around there. My sketch might not be the best, but we'll just say it's around there, right? So the midpoint here, let's make a note then. So the midpoint here of PQ is the center of C. Okay, so let's just start then by finding the center of C here. So for the midpoint here, what we simply need to do here then is average the x coordinates here and also average the y coordinates. So nice and straightforward, right? So what I get here then is -6 plus 4. So -6 plus 4, because we're averaging here the x coordinate, sorry. What we do then is simply divide by 2. And we just do the same here, right, with the y coordinate. So -1 plus 1 over 2. Okay. What we obtain here then is, so I get -2 over 2, that's -1. I get 0 over 2, which just gives us 0. Okay, so the midpoint here actually is there. So I'll do that in a different color. Let's just do it in orange here. So that would be, say, there, right? So that's -1, 0. As you can see, my diagram isn't perfect, but it looks close enough. So that there is -1, 0. Okay. Now, what we also need here then is the radius, right? If we want the equation of C. So for the radius here, all I'm going to do then is just find the distance between my center here and any of these 2 points. Okay. So for my radius here then, this would be the square root of, so what I'm going to do here then is 0 minus then -1. We square that, right? So I get 0 minus -1 all squared. And we now do the same here then with the x coordinate. So what I'm going to get here then is -1 minus -6 all squared. So -1 minus then -6 all squared. Okay, let's just simplify this here. So again, all I'm doing here then is finding the distance here between this point and this point here, but you could also do it with these 2 points here. Again, that's absolutely fine. You should get the same here for the radius. So 0 minus -1, that is 1, so I get 1 squared, plus, I don't know why I've done the square root so big here, but it doesn't matter. So -1 minus -6, that is -1 plus 6, so I get 5 there. So 1 squared plus 5 squared, that gives me the square root of 26 here. Okay, so this here then is the radius r, so r is equal to the square root of 26. So for an equation here of C, right, rather than the equation, let's just write this down here. So therefore, C has equation So what I'm going to do here is use x minus a all squared plus y minus b all squared is equal to r squared. Okay, let's just make a note here. So using this x minus a all squared plus y minus b all squared is equal to r squared. Okay, in that case then what I get here is, so I get x plus 1 all squared, right? Because my midpoint here is minus 1, so it's the opposite of this. So I get x plus 1 squared. So x plus 1 squared. The y coordinate here for the midpoint is 0, so I just simply get y squared here. So plus y squared. And this here then is equal to r squared. So if r is the square root of 26, r squared here is simply 26 there. Okay. And there we have it then. So this here gives us the solution to part A. So for the very last part then of question 4 here, all we want to do is find an equation of the tangent to the curve C at the point P, giving your answer in this form here where M and C are constants to be found. So for part B then, let's just do this underneath here. Where do we begin then? Well, what I'm looking for here is the equation of the tangent to the curve C at this point P here. So if I just quickly do it in a different color, let's just do it in, say, green here. And what I'm looking for is the equation of this straight line here, right? The tangent to the curve C at the point P. And that would look, say, something like this. Now, clearly it should be a straight line, but you get the idea, right? I want the equation of this line here. So clearly, I can see straight away that the gradient here must be negative, right? So to begin with, how do we obtain that gradient there for the straight line here, the tangent, right? Well, what I need to do to begin with here is find the gradient then between this point here, P, and the center here. Okay, let's just make a note here then. So the gradient between the center, so between center and P is given as, so it's M here, right, for the gradient, is equal to y2 minus y1 over x2 minus x1. So I'm going to take y2 here as 0. It's going to be 0 minus them, minus 1. So 0 minus 1 all over. So it's going to be minus 1 here. So minus 1 because minus 1 here is my x2 minus then x1 here, okay, which in this case is minus 6. So x2 minus x1 is minus 1 minus then minus 6. Okay, so obviously just be very, very careful here with the signs. So 0 minus minus 1 is just the same as 0 plus 1. So we get 1 there for the numerator. And now for the denominator here, I get minus 1 minus minus 6, which is just the same as minus 1 plus 6. So I get 5 there for the denominator. Now, just be slightly careful here. This is not the gradient that we require, right? This here is the gradient, and again, I'll just do it in a different color of, what color can I do it in? We'll do it in light blue here. So 1 over 5 here is the gradient of this line segment here. But I don't want the gradient of this line segment here. I want the gradient of this green straight line here. So this would be the negative reciprocal gradient here, right? The perpendicular gradient. So my perp gradient here, so my perpendicular gradient then is, so we flip this and times it by minus 1. So I get 5 over 1 times that by minus 1. I get minus 5 there. Okay. And then finally to finish with here, what I need to do then is use y minus y1 is equal to m times x minus x1. Okay. Obviously, just be careful here what you choose for x1 and y1. This must be the point P, right? So if you choose the coordinates of Q here, you're going to get this wrong. Okay, so just be very, very careful for that. So what I get here then is to get y minus y1, where y1 is minus 1, so y plus 1 here is equal to m, where m is minus 5, times x minus x1, where x1 here is minus 6. So I get x plus 6 there. Okay, let's expand here the right-hand side. We've got y plus 1 is equal to minus 5x minus 30. And then finally, right, if we want it in this form here, y equals mx plus c, all I now need to do here is just subtract 1 from both sides. And in that case here, we obtain that y is equal to minus 5x, and then minus 30, minus 1, that gives us minus 31 there, okay? And there we have it then. So that gives the solution here to part B and the solution to question 4. Now for question 5 here, we want to show the following. Now, at first glance here, this might look a little bit scary and maybe even intimidating. But to be honest, this is really, really straightforward stuff. I just think because this doesn't come up every year, there is a bit of a tendency here to throw students and seem a little bit trickier than it actually is. But this here is just basic year 1 integration. Okay. So what I need to do here is just rewrite this summation as an integral. We're going to integrate here. Okay. So what we've got here then is the integral of, so it's x times x plus 1 over x to the 3 over 2 plus 1 all over x to the 3 over 2. We're integrating here then with respect to x. As we can see here, we had delta x, so this now becomes dx here. And our limits of integration are from 1 to 2. So as you can see then, converting this from a summation to an integral is actually pretty straightforward. And the actual integral here, again, is straightforward. So to begin with here, let's just simplify the numerator. So let's just expand out and add these two terms together. So what I've got here then is, I've got x squared plus x plus 1 all over x to the 3 over 2. Again, we're integrating here with respect to x, and our limits of integration don't change. So from 1 to 2 there. Okay. So at this point here, let's just simplify our integrand. So what we've got here then is the integral of, so I've got x squared over x to the 3 over 2. So that would just simplify to give me x to the power of a half. So I've got x to the power of a half. I've then got x over x to the 3 over 2. That just simplifies to give me x to the minus a half. So x to the minus a half there. And then finally 1 over x to the 3 over 2. That's just simply x to the power of minus 3 over 2. So plus x to the minus 3 over 2 there. Okay, again, integrating here with respect to x. And again, our limits of integration do not change. Okay, so now let's actually evaluate this integral here. So simply add 1 to the power, divide by the new power, right? So what I get here then is the following. So I get x to the 3 over 2 divided by 3 over 2. So x to the 3 over 2 over 3 over 2. I then get, so this would be minus, in fact, it would be plus actually. So x to the 1 over 2, x to the 1 over 2, all over 1 over 2. And then finally, this one here would be negative. So minus x to the minus a half then, all over 1 over 2. Okay. From 1 to 2 again. And let's just simplify this here then. So inside the square bracket. So obviously you could have done this all in one step. I'm kind of showing all steps as I go, but it really doesn't matter. So here I get 2x to the 3 over 2 over 3. I then get 2x. So 2x power of a half. Then I get minus 2x to the power of minus a half. Okay, from 1 to 2. Okay, and at this point here, this looks a lot better, right? So to finish with here, all we now need to do then is just substitute in our upper limit and also substitute in our lower limit, right? So let's just do that over here. So what am I going to get here then? I get 2 lots of 2 to the power of 3 over 2 over 3. So that is the square root of 2. We then cube that. Then we times it by 2. So altogether here, what I'm going to get then is, I get 4 root 2 over 3, because 2 to the power of 3 over 2 is 2 root 2. Times it by 2, you get 4 root 2. So 4 root 2 over 3. So this here then is going to be 2 root 2. So all I'm doing here, right, is just substituting x equals 2 into each expression here, or each term as I go. So 2 root 2. And then finally what I get here is minus 2 over root 2. So this here then is my upper limit. We now subtract the lower limit. So for the lower limit here, this is when x equals 1. So I get 1 to the 3 over 2, so that's just 1. Times it by 2, divided by 3. So I get 2 over 3. So 1 to the 1 over 2 is just 1. Times it by 2, I just get 2. And we then get minus 2 here. So minus 2 there. Okay. So let's just simplify here. Well, they just cancel, like so. I've got 4 root 2 over 3 plus 2 root 2 minus 2 over root 2. Now, minus 2 over root 2, just make a note here. So 2 over root 2 is just the same then. Once we rationalize here, I get 2 root 2 over 2. The 2's just cancel. We simply get root 2 there. So what I've got here then is, 4 root 2 over 3 plus 2 root 2 minus root 2. Okay. And also don't forget here the minus 2 over 3. Like so. So we're nearly here now at our solution. So 2 root 2 minus root 2, that just gives me root 2. So 4 root 2 over 3 plus root 2. Let me just make a note here. So 4 root 2 over 3 plus root 2. So that would be, so we get that over a common denominator here. So plus root 2. So over a common denominator here, that must be 3 root 2 over 3. 3 root 2 over 3 there. Add those together. What I get here then is, so we get 7 root 2 over 3. Like so. And then finally, minus 2 over 3 there. Okay. Perfect. So if we now identify the value of a and b here, as we can see then, a here is simply 7 over 3. And b here is minus 2 over 3. Okay. And there we have it then. So something that looks quite tricky and a little bit challenging here actually just boils down to basic, straightforward year 1 integration, right? Just get it into the correct form here, a root 2 plus b, as we've obtained here. So a equals 7 over 3 and b is equal to minus 2 over 3 there. Okay. So there we have it then. That gives us the solution here to question 5. Moving on to question 6 here then, where we have Bill and Bob. So Bill and Bob are both using deposit savings schemes over a 48-month period. So for Bill then, Bill saves £80 in the first month, and in each subsequent month, he will deposit £10 more than the previous month. So in the second month then, he deposits £90, £100 in the third month, and so on, forming an arithmetic sequence. So for the first part of this question then, part A, what do we want to do here? So we want to find the amount that Bill deposits in the 24th month. So all we're looking for here then is just the 24th term, right, in this arithmetic sequence. So this here would be U24. So all we need to do here then is just use the formula for the nth term here of an arithmetic sequence, right? Which in this case here, let's just make a note then. So UN here is equal to, so it's A plus n minus 1 times D. Nice and straightforward, right? So what is A here? So let's just make a note then. So A here, our first term is 80. The common difference here, D, is 10. And N here is 24. Okay, so let's just put all of that here, or all of this here into this here. So I've got A, which is 80, plus n minus 1, so 24 minus 1, which is 23, times that by d, which is 10. So I get 230 plus 80. Nice and straightforward then. We simply get 310 there. Nice and easy, right? Now for the next part of this question, part B, we now want to find the total amount that Bill deposits over a 48-month period. This should be capital B, by the way. I'm just a slight pedantic point there. It is a name, but just ignore me, I'm rambling. But anyway, for part B, what do we want to do here? So we want to find the total amount that Bill deposits over the 48-month period. So what we're looking for here then is the sum of the first 48 terms, right? So again, all we're going to do here is use the correct formula. So for the sum of the first n terms here, again, let's just make a note. So the sum of the first n terms here is n over 2 times by 2a plus n minus 1 times d. Okay. Again, a, d, and n here. Well, a and d are the same. N will change now to 48, right? Because we're looking for the sum of the first 48 terms. So what I've got here then is 48 over 2 because n here now is 48. We've got 48 over 2. Then times it by 2a. So a is 80, so 2 lots of that is 160. Plus, we've got n minus 1 here, so n is 48. Subtract 1, we get 47. And then we times that by 10. Okay. At this point here, just put all of this into your calculator. And if you do this correctly here, then what you should obtain is 15,120. Okay. Given that we are talking about money here, I should probably put the correct currency symbol here. So £310 and £15,120 there. Okay. So there we have it. That gives us the solution to part B. Now, for the next part of the question here, we're now looking at Bob's savings scheme. So Bob's savings scheme starts by depositing £480 in the first month, and in each subsequent month, he will deposit £10 less than the previous month. So what that means then is in the second month, he deposits 470, 460 in the third month, and so on, again, forming an arithmetic sequence. We're then given that after n months, Bob will have saved 11,660 for his deposit. So for part C then, it says by forming an equation in n, show the following. Right, so where do we begin here? So for part C then, what we're basically told here is the sum of the first n terms here using this arithmetic sequence here is equal to this amount here. So 11,660, right? So for the sum of the first n terms here, that's this formula. I've got n over 2. Now, let's just be slightly careful here. So don't forget, right, a and d are different for this arithmetic sequence. So what have we got here? So a is 480. That's our first term. And d here, the common difference, right, is minus 10. We deposit £10 less every month. So d is minus 10 there. So 2a then is going to be 480 times 2, so that's 960. We get 960 plus n minus 1, right? Because we don't know what n is, so just keep that as n. So plus n minus 1 times by d here, which is minus 10. So times by minus 10. And this here then is equal to this number here, 11,660. Okay, so there's two ways to go about this. You can just times through by 2 here. That's absolutely fine. Or just expand this bracket here on the left-hand side. I'll just expand this bracket here on the left-hand side. So what we're going to get here, so I've got 960 times by n over 2. So I get 960n over 2, which just gives me 480n. So 480n there. We'll expand this bit here. So n times minus 10 is minus 10n. So if I times that then by n over 2, I get minus 10n squared over 2, so that's minus 5n squared. So minus 5n squared. And then minus 1 times minus 10, just be careful of your signs here, right? That's positive 10. But then get 10n over 2, which is 5n. So plus 5n there. And this here is equal to 11,660. So let's just keep cleaning this up here. What I'll do here is take the minus 5n squared over to the other side. I've got 480n plus 5n, so that's 485n. So we'll also subtract 485n off both sides here. So altogether then, what I get here is, so we get 5n squared. So 5n squared minus 485n. And I've also got this 11,660 here, right? So plus 11,660. And all of this here is equal to 0. And what we can do here then, given that each coefficient here is a multiple of 5, is just divide through by 5, right? So what I get here then is n squared. So minus 485 divided by 5, that gives me minus 97. I get minus 97n there. And then 11,660 divided by 5 gives me 2,332 there. Okay, and this here is equal to 0. And just notice here then, this is exactly what we wanted to form here, right? This is our equation in n. So as required there, and part C complete. Good stuff. So there we have it. That gives us the solution to part C. Now for part D then, let's just read the question here. All we want to do then is just solve the equation in part C. So even if you couldn't derive this quadratic equation here, you can still go on to answer part D and part E, right? So just keep an eye out for things like that in your actual exam. Don't be put off even if you can't answer things like this. So solving this quadratic equation here, nice and straightforward, right? Just simply put this into your calculator. We don't need to make this complicated or anything like that. Just put this here into your calculator. And what you'll find then is this actually factorizes here. So what I get then is n minus 44 times n minus 53. And this here is equal to 0. So in that case, then we get two solutions for n here. So we get n is equal to 44. And we also get that n is equal to 53. Okay, so nice and straightforward then. That is simply the solution to part D. And then finally, to finish with here, we have the very last part of this question. So for part E then, all we want to do here is state which value of n is not a sensible solution to this equation here. Now for part E then, if we think about the context of this question here, which of these solutions is not sensible? Well, that would be this solution here, n equals 53. So n equals 53 is not sensible, and the reason for that is because the money has already been saved after 44 months, right? So n equals 53 is not sensible because, or as the money is already saved after 44 months. Okay. And there we have it then. Obviously, oops, that's supposed to be an exclamation mark. Obviously, there's a few different things you could kind of put here for part E, but anything that makes sense and is a sensible kind of conclusion here is absolutely fine, right? As you can see, just one mark for this. It doesn't need to be a novel. Just one kind of succinct point here is absolutely fine. Okay. But there we have it then. So that gives us the solution here to part E and the solution to question 6. So for the next question here, question 7, we're given the curve C, which is given parametrically as the following. And all we want to do here then is show that dy by dx here is equal to 1 minus x all over 1 plus y. We need to show all of our working. So we've got parametric differentiation here, right? So to begin with here, let me just quickly write down the parametric equation. So x equals 1 plus 2 cos theta. And y here is minus 1 plus 2 sine theta. Okay. And this is for theta between 0 and 2 pi. So I want dy by dx here. So dy by dx then, let's just make a note here. So dy by dx then is equal to dy by d theta. So dy by d theta all over dx by d theta. So to begin with then, let's find dy by d theta and also dx by d theta. So in that case then, dx by d theta here, what would that give us? So just differentiate x here with respect to theta. Nice and straightforward. Then we simply get minus 2 sine theta. So minus 2 sine theta there. Okay. And then for dy by d theta here, that would be our numerator. What do we get here then? So dy by d theta here. Again, just differentiate y with respect to theta. So again, nice and straightforward here. We simply get 2 cos theta. So 2 cos theta there. Okay. And in that case then, as we've just mentioned here, dy by dx is equal to dy by d theta all over dx by d theta. So we'll continue down here. So therefore, dy by dx here is equal to, so dy by d theta is 2 cos theta. So we get 2 cos theta all over dx by d theta, which is minus 2 sine theta. So minus 2 sine theta. Okay. Now, what we want here is 1 minus x all over 1 plus y. And I think at this point here, this is where this question could become a little bit more difficult for some students. Okay. How do we obtain this required form here? Well, we go back to the original parametric equations here, right? I've got 2 cos theta here, and I've got 2 sine theta here. Now, we want minus 2 sine theta. So, to begin with then, let's just rearrange here. So, 2 cos theta is equal to x minus 1. So, x minus 1 there, nice and straightforward, right? And then for minus 2 sine theta, so for minus 2 sine theta, so just rearrange this equation here then. So we subtract 2 sine theta off both sides, right? And subtract y off both sides. Then this is minus 1 minus y. Okay. So in that case, then what I get here is 2 cos theta, which is x minus 1. I get x minus 1 there, all over. That is supposed to be a minus. It's not the best though. We'll do it properly. We do things proper around here, right? So x minus 1. It's not much better, but it'll do. So x minus 1 over minus 2 sine theta, which is minus 1 minus y. There we go. Much better. So minus 1 minus y. Perfect. Now, we're getting pretty close to what we want here, but it's still not quite right. So what do we do next here? So what I'm going to do here then is just factor out a minus from both the top and bottom here, right? Essentially just factoring out minus 1 from both my numerator and my denominator here. So what we're going to do here then is essentially just factor out minus 1 from both the numerator here and the denominator, right? So for the numerator then, I get minus here. So all that's going to happen then is the signs will flip here. So I get 1 minus x. So 1 minus x there. All over. Doing the same here with the denominator again. Signs will just flip here. We get 1 plus y. Okay. And because I've got minus over a minus here, the minuses will just cancel. And in that case then, in fact, let me just do it underline underneath here. So in fact, we'll just get rid of that. We're getting there. So dy by dx here is equal to 1 minus x. There we go. 1 minus x all over 1 plus y. And just notice here then, this is exactly what we wanted here, right? So as required there, and perfect. So quite a small question, right? And as we can see, only 5 marks for this, so not tons of work. But yeah, there we go, right? So let me just quickly clean this up here, so it looks a little bit neater. There we go. Perfect. Bosh, good stuff. Okay. So there we have it then. So hopefully nothing too challenging there, but that gives us the solution to question 7. Let's have a go then at question 8 here. So for question 8 then we have figure 1 below. It shows a sketch of the graph with this equation here where a is a positive constant. We're then told that the graph intersects the y-axis at the point A, which we can see here. It intersects the x-axis at the points B and C. Again, we can see that here on our diagram or figure 1. And then finally it has a minimum point at D. Okay. So for the first part of this question then, part A, we want to find here in their simplest form in terms of A, the coordinates of the following. So for point A then, let's just do that underneath here. So for point A then, as we can see, right, this here is when x equals 0, okay? It's the y-intercept, in other words. So this is when x equals 0. So when x equals 0, so what do I get here? So all we need to simply do here then is just substitute x equals 0 into this equation here. So y is equal to, so I get minus 3a, sorry, the modulus of minus 3a here, I should say, like so, minus a, okay? So the modulus of minus 3a is 3a, so 3a minus a, that gives us 2a there, okay? So the coordinates here then of the point A are simply 0, 2a there, okay? Hopefully nice and straightforward there for the first part. Now for the next part here, so this is a part 2, this is the coordinates of the points B and C. So points B and C here, okay? So this is the x-intercept here, right? So in other words, when y is equal to 0. So when y equals 0, okay? So what do we get here then? Well, all I do here then is set y equal to 0. So I get the modulus here of 2x minus 3a minus a is equal to 0. So in that case, then what I get here is 2x minus 3a minus a is equal to 0. So minus 3a minus a is minus 4a. Take that over to the other side. So 2x is equal to 4a. Divide both sides by 2, right? And x in this case here is equal to 2a. Have I made a mistake here? Oh, no, that's fine, right? X equals 2a. Perfect, that's fine. And then we also have the negative part here of the modulus function. So in that case then, rather than it being 2x minus 3a, this would be minus 2x plus 3a here. That's the negative argument of the modulus function. This one here was the positive argument, okay? So I get minus 2x plus 3a minus a is equal to 0. So minus 2x plus 2a is equal to 0. In that case, then 2x is equal to 2a. Just divide both sides by 2, right? So x here is equal to a. Okay. So if a is a positive constant, then clearly 2a is greater than a. So this one here corresponds to 2a. This one here corresponds to a. So what I'll do here is I'll state these underneath. So the point B then, that has coordinates of a and 0. And then for C here, this is 2a and 0 there. Perfect. Okay. And then finally, for the very last part here of part A, this is for the coordinates of point D, right? So for A part 3, this is for point D. Now for the point D then, let's just think about this for a moment here. So this is the minimum point. Now, the minimum point then must occur here when the modulus function is equal to 0. So in that case then, the modulus here of, well, not the modulus, sorry, we can get rid of the modulus here. The inside here must be equal to 0, right? We want the modulus of 0. So 2x minus 3a is equal to 0. Just solve for x here, right? So 2x is equal to 3a, and therefore x is equal to 3 over 2a, like so. And now for the y coordinate here, well, that would simply be minus a, right? This part here is 0, so my y coordinate then is minus a. So for the coordinates then of the point D, in its simplest form in terms of a, let's just write this, kind of run out of room here, so I'll just kind of do it above. So D here then has coordinates of 3 over 2a and also minus a there. Okay, so to make a note here, I'll do it in a different color. So this was the solution to a part 1. This here is the solution to a part 2, so that's B and that's C. And this here then is the solution to a part 3, right? That's the coordinates of D there. So there we have it then. That gives the solution to part A. Now, as we can see then, we've kind of run out of room here. So let me just quickly pause the video, clear the screen, and then we can have a go at answering part B. So as we can see that we've now cleared the screen here, so let's just have a go then at answering part B. So for part B then, what do we want to do here? So we want to find then, in their simplest form, in terms of a, the values of x for which, and then we're given the following modulus equation here. So let me just start then by writing down this modulus equation here. We've got 2x minus 3a minus a is equal to the modulus of x minus a. Okay? So what we're going to do here, as we did then for the points B and C here, is consider both the positive and negative arguments here of our modulus functions, right? And if we consider the positive argument here, we do that for both of them at the same time, and the same applies for the negative argument, okay? So let's just start then with the positive argument here. In that case, then what I get here, in fact, let me just make a note. So positive argument. So for the positive argument here, what I get then is 2x minus 3a minus a is equal to x minus a here, okay? So all we need to do here then is just solve for x, right? So hopefully pretty straightforward. On the left-hand side, we get 2x minus 4a is equal to x minus a. Add 4a to both sides, subtract x off both sides here. So if we do that then, I get minus a plus 4a, so that's 3a, and then 2x minus x just gives us x. So in that case then, x here is equal to 3a. And there we have it, right? So that's the positive argument here, but we're not done because, as we mentioned before, we also need to consider here the negative argument. So for the negative argument here, this is now basically the opposite signs here within my modulus function. So I get minus 2x plus 3a and minus x plus a here, okay? So let's just write that down then. So I get minus 2x. So minus 2x plus 3a. Don't forget the minus a as well here. Very easy to forget. Is equal to minus x plus a. Okay. Again, all we need to do here is just solve for x. So on the left-hand side, I get minus 2x plus 2a is equal to minus x plus a. So let's just add 2x here to both sides and also subtract a off both sides here. So minus x plus 2x, that just gives me x here. To obtain x here, and then 2a minus a, that just gives us a here. Okay, and in that case then, x is equal to a. So my solutions here, in their simplest form in terms of a, or in other words, the values of x for which this following modulus equation holds here, is given as x equals a, and also x equals 3a. Okay, and there we have it then. So that gives us the solution here to part B, and the solution to question A. So moving on to question 9 here, where we want to use a suitable trigonometric identity to find the following integral. Now, as we can see, just 3 marks for this. We shouldn't really be expecting too much work, right? So let's just start then by writing down this integral here. So what we've got then is the integral of 1 all over 1 plus cos 2x. I'm integrating here then with respect to x, right? Now, as the question suggests here, we do need to use a suitable trigonometric identity. So the only thing that we can do here is work with cos 2x, right? It's the only trigonometric term that we have. So what is cos 2x here? Identical to. So obviously there's a few different things that you can put here. But what we're looking for then is 2 cos squared x. So 2 cos squared x minus 1 here. And what will happen then is once I replace cos 2x with 2 cos squared x minus 1, this 1 here and the minus 1 will cancel, and things will start to fall out quite nicely in terms of evaluating this integral here. So let's just rewrite this integral here then, using our trig identity, right? So what I've got here then is 1 all over 1 plus cos 2x, which is 2 cos squared x minus 1. So plus 2 cos squared x minus 1. Don't forget the dx as well, right? That's a bad habit of mine. So let's just keep going then. So like we just said, right, this 1 here cancels with this minus 1. And what we've got here then is the integral then of 1 all over 2 cos squared x dx. Now, if we've got 1 over cos squared x here, we have sec squared x, which is one of our standard results, right? So if I've got 1 over 2 cos squared x here, and we're integrating with respect to x, I can write this integral here then as the integral then of a half sec squared x. We're integrating here then again with respect to x. And as we've just mentioned here, right, this is one of our standard results. So a half sec squared x here with respect to x then, the integral of that would simply be a half tan x. And of course, given that we don't have limits here on our integral, do not forget our constant of integration there, plus c. Like so. And there we have it then. So hopefully quite a nice question there, just kind of thrown towards the, the middle end. Towards the middle of the paper. Just gives a bit of a break from some of the longer questions and more context-heavy questions. But there we have it, right? So hopefully nice and straightforward there, giving us a solution to question 9. Let's just have a go then at question 10 here. So for question 10 then, we're given this function g of x. We're also given that g of x can be expressed in this form here. So basically, this is just a partial fraction decomposition of this algebraic fraction here. And then for the first part of this question here, part A, what we want to do is find the values of a and b. So for part A then, partial fraction decomposition here should hopefully be pretty standard stuff in terms of your revision and answering questions like this. So the first thing that we do here then is get the right hand side here over a common denominator. So in that case then, what I get here is a times x plus 2. And then we get b times by 2x plus 1. And this here then will be equal to x plus a. Okay. Now at this point here, what we want to do is eliminate both a and b. Obviously, we'll do that separately. So if we eliminate a, for example, we can then go on to solve for b and vice versa. Okay. So for example then, if we let x equal, say, minus 2 here, okay? So if x equal to minus 2, then what I get here is a times minus 2 plus 2, which is 0. So a times 0 is just 0. So in that case there, we've eliminated a, and we can go on to solve for b, okay? So 2 times minus 2 is minus 4, plus 1 gives us minus 3. So I get minus 3b is equal to minus 2 plus 8, which is 6. Divide both sides by minus 3, and we obtain that b is equal to 6 over minus 3, giving us minus 2. And in a similar fashion here then, if we let x equal, so let x be equal to So if x is equal to minus a half here, let's think about that for a moment. So if x is equal to minus a half here, then what would we get here? So b now would disappear because 2 times minus a half is minus 1 plus the 1 is 0. B times 0 is just 0, right? So I get minus a half plus 2, so that's 3 over 2. We get 3 over 2a is equal to, so minus a half plus a, that is 15 over 2. So 15 over 2 divided by 3 over 2. In that case, then what do we get here for a? So therefore a is equal to 5. Okay. So to finish with here then, well, it doesn't actually ask us to express it in this form here. So all we want to do is find the values of a and b. So that's absolutely fine, right? So a here is equal to 5 and b is equal to minus 2. Perfect. Okay. So that gives us the solution there to part A. Now for the next part of this question here, part B, what do we want to do here? So it says, hence or otherwise, find the series expansion of g of x in ascending powers of x up to and including the x squared term. We need to simplify each term here. Now, these questions can be quite lengthy. I'm hoping I do have just about enough room here to answer part B as well. We'll give it a go anyway. We'll see where we get up to in terms of room left to answer the question. So I want the series expansion here then of g of x, right? That's this function here. Now, in this form here, obtaining the series expansion is not pretty. However, if we use this result here that we've just obtained then from part A, it becomes a whole lot easier, right? So g of x here then, let's just write this out given its partial fraction decomposition here. That is 5 over 2x plus 1. So 5 over 2x plus 1 plus b over x plus 2. So b then is minus 2 here. We get minus 2 all over x plus 2. Okay. So what I'm going to do here is think about this in two different parts. I've got this part here, so 5 over 2x plus 1, and also minus 2 over x plus 2. Okay, I said minus 2. We'll just think about this as positive, so 2 over x plus 2. And obviously the series expansion of the full thing here would be the series expansion of this fraction here minus the series expansion of this fraction here. Okay. So what I can do here then is also use indices here to rewrite both of these fractions. So what I've got here then is 5 bracket 2x plus 1 to the minus 1 minus 2 bracket x plus 2 again to the power of minus 1. Okay. So what I want here then is the series expansion of 5 bracket 2x plus 1 to the minus 1. So in this case here, because it's 1 as the constant term here, then we can go straight into using the binomial expansion as it's given in your formula book. I did forget to include it here as part of the question. So just grab your formula book if you don't know it to heart. But either way then, what should we get here? So let's continue over here on the left-hand side, just so we've got a little bit more room here to answer part B. So 5 times by this here. So I've got 5 bracket. I'm going to get 5 bracket 1. We then get minus 1 times by 2x here. So minus 1 times 2x, like so. We then get minus 1 times minus 2. That's all over 2 factorial. And what we do here is we times this by 2x all squared. So 2x all squared there. Okay. We're only going up to the term in x squared, or the x squared term. So that's absolutely fine here for the series expansion. Okay. So we'll close that bracket and let's just quickly simplify this here. So what do we get then? So I get 5 times by 1. In fact, before I do 5 times anything here inside this bracket, let me just clean up everything inside this bracket here. So I get 5 bracket. So 1. I've then got minus 1 times 2x. That's minus 2x. I've then got minus 1 times minus 2. So that's 2 over 2 factorial, which is also 2. So I've got 1 here times 2x all squared. So that's plus 4x squared there. Okay, so we get 1 minus 2x plus 4x squared. So if we now times through by the 5 here on the outside, what we get then is 5 minus 10x plus 20x squared. Perfect. Okay. So that is the first series expansion there. Now for the next one here, a little bit more complicated because rather than it just being plus 1 here, it's plus 2. So we do need to factor that out. Okay. So let's just go here step by step. So we've got 2 bracket x plus 2. Okay. So the minus 1 here, I don't know why I've kind of written this out over here, but we'll continue anyway, just because I do need to factor out the 2. So what I get here is 2 bracket. So we now factor out the 2 here. So 2 on the outside. On the inside, then, this now needs to be x over 2. X over 2. And this here then becomes plus 1. Perfect, right? That's what we want here. And this is all to the minus 1 here. Okay. So, what do we get here then? So, I've got 2 to the minus 1, which is just the same as 1 over 2 or 0.5 here. And then I times it by the 2 on the outside. So 2 times by 1 over 2, they just cancel. I just get left with this here then. So x over 2 plus 1, the power of minus 1. Okay. So what is the series expansion here then of this? So what I'm going to get here then. So we get, so I'm going to get 1 plus, we then get minus 1 times by x over 2. Like so. Obviously, we only need to do this one more time here because, again, we're going up to the term in x squared, or the x squared term here. So I get minus 1 times minus 2. Again, that's all over 2 factorial. What I do here then is I times this by x over 2 all squared. Like so. Let's just simplify this here. So I get 1 minus x over 2. I've got minus 1 times minus 2. So again, that's 2 over 2 factorial, which again is just 2. So that just gives me 1 there. And then x over 2 all squared is x squared over 4. So plus x squared over 4. Okay. So for the series expansion here of g of x then, what it's going to be is this expansion here minus this expansion here, right? That's what we've got here. Just make a note of that here. So let's continue up here. So therefore the series expansion. So the series expansion of g of x is, so we just said then, it's this here. So 5 minus 10x plus 20x squared minus them. So 1 minus x over 2 plus x squared over 4. Okay. I'll also put this inside a bracket here just so it's kind of clear what I've done. Let's get rid of the subtraction here, or the minus sign. Put the brackets in just so you can see everything in full here, like so. So, oh, I made a mistake here. Something doesn't look quite right. No, I think that's fine, right? So 5 minus 1 is 4. Perfect. I've then got minus 10 minus x over 2. So this is just the same as doing minus 10 plus a half. So minus 10 plus a half here. I'll just do it on my calculator just so I don't make a mistake because I am guaranteed to do that. I'll try to do it off the top of my head. So minus 10 plus a half. That gives me minus 19 over 2. So minus 19 over 2x there. And then finally 20 minus 1 over 4. So 20 minus 1 over 4. And that gives me 79 over 4 there. So is it plus? Yeah, plus. So plus 79 over 4 x squared. And obviously this will just keep going on and on, but we're only concerned about going up to the term in x x squared. So at this point here, question complete. So what I'll do here is I'll just quickly kind of box this off so you can see what the solution is here. Okay. And there we have it then. So this here is our solution. Happy days. So fingers crossed I've not made any tiny little errors with this question here. Binomial expansion is my worst nightmare for making mistakes. It is really, really easy to be fair. So as you work through exam questions on the binomial expansion, do just take care as you work through the question, right? Don't make a mistake, as I often do. But there we have it, right? So hopefully not too challenging there in terms of difficulty. But there we have it. So that gives us the solution there to question 10. Now for the next question here, we have question 11. And what we're given here is the function f as follows. And the function f then can be used to model the price of a car in pounds t years after it's purchased. Now for the first part of this question, then part A, all we want to do here is find f prime of t. So hopefully, nice and straightforward here just to get us started. So f prime of t then, the only thing to really be careful of here, or just be considerate of, is this 0.75 to the power of t, right? Once we differentiate with respect to t here. So what we get then is 12,000 times 0.75 to the t, and then we times this here by ln of 0.75. So ln of 0.75, like so. And the minus 800 cos t here, that differentiates, it goes plus 800 sine t. So plus 800 sine t there. And there we have it. So nice and straightforward. That gives us the solution here to part A. Now for the next part of this question, and what we're given here is the equation f of t equals 0 has a root alpha in this given interval here. So for part B then, what we want to do here is take 11.5 as a first approximation, and then apply the Newton-Raphson method again here to obtain a second approximation for when the value of the car is 0, giving your answer to 4 significant figures here. Now for part B then, all we're going to simply do here is just use the given result here for the Newton-Raphson method, right? Don't forget, this is also given in your formula book. So what we're working with here, right, is t of n plus 1, right? That's the next term here, given that we're working with t as opposed to x. It doesn't really make a massive difference, but we'll keep it consistent with the question. So in that case then, what I've got here is t of n plus 1 is equal to, so it's t of n, the previous term, minus f of tn all over f prime of tn, right? I've just adapted this formula here in terms of t, right? Nice and straightforward. And t1 here, so t1 here, our first approximation is 11.5. So what I need to find here then is f of 11.5. So f of 11.5 and also f prime of 11.5. Okay, so all we need to do here, right, is just substitute 11.5 into f of t and also f prime of t, right? Should hopefully be nice and straightforward, so just simply use your calculator here. If you do this correctly then, for f of 11.5, what you should get here is 52.27660,183. So this here then is every figure given on my calculator display. And then for f prime of 11.5 here, again, if you do this correctly, what you should get here is minus 826.6312726. And again, this here is every figure as it's given on my calculator display. And at this point here then, we now have everything that we need then to find T2, right? Our second approximation for when the value of the car is 0. So T2 here is equal to T1 minus f of T1 all over f prime of T1. So T2 then is equal to T1, which is 11.5, minus here f of T1, which is 52.276, so on and so on. So let's just write this down in full here. 276.60183 all over then f prime of T1, which is f prime of 11.5, right, which is this number here. So again, let's just write this down in full. 6312726. Okay. And at this point here, just put all of this into your calculator. And if you do this correctly here, then what you should get is 11.56324053. And then, as the question asks for here, right, to 4 significant figures, what we're going to get here then is simply 11.56, right? So we get 11.56 there to 4 SF. Okay, and there we have it then. So that gives the solution here to part B. And now for the very last part then of this question here, part C, right, just says comment on the suitability of this model for the value of older cars. So the issue here then is that for cars approximately 12 years or older, the model is not going to be suitable, as the car cannot have a negative value, right? So let's just make a note of that here then. So for cars, approximately, let's put approx here, 12 years or older, the model is not suitable as the car cannot have a negative value. Okay, and that's all we need there, right? As you can see, it's just simply 1 mark. We don't need a novel or anything like that. Just one quick point there, just to finish with our question 11 there, right? So there we have it then. That gives us the solution here to question 11. Now for question 12 then, what we're told here is the population p million people of a country is first measured in 1970. Now the equation p equals ab to the t here, where a and b are constants, models the population t years after 1970. And then what we're given here is the population for 2 different years. So the population then was 52 million in 1990 and 87 million in 2020. So for A part 1 then, here, what we want to do then is find the value of b to 3 decimal places. So where do we begin here? Well, what I can do to begin with here then is just make a couple of notes here. So if the population was 52 million in 1990, what that tells me here then is P is 52. That's the population here, P, right? P million people. And then T here, well, T is T years after 1970. So if it's 1990, T is equal to 20. Doing the same here then for the second bullet point here, 87 million in 2020, then P here, the population is 87, and T here, well, 2020 is 50 years after 1970, so T then is 50. And using this information here and the given equation, so P is equal to AB to the T, and what we can do here is form equations, right? In that case then, using this information here, AB to the 20 is equal to 52, and then AB to the 50 is equal to 87. Okay? So we call this equation 1, we call this equation 2 here. What I'm going to do then is take equation 2 and divide that by equation 1. Okay? So in that case then, what I get here is AB to the 50 over AB to the 20. So AB to the 20 And this here then is equal to 87 over 52. So 87 over 52 here. Now clearly the a's just cancel here, like so. I've got b to the 50 over b to the 20, so just basic rules of indices here, right? I get b to the 30. So b to the 30 then is equal to 87 over 52. Like so. Now we just want the value of b here, right? We want the value of b to 3 decimal places. So for b then, b here is the 30th root of 87 over 52, or just simply 87 over 52 to the power of 1 over 30, whichever way you prefer to write that, right? So, like we said, you can either write this as the 30th root of 87 over 52, or 87 over 52 to the power of 1 over 30. Either's fine. Either way, you'll get the same answer. And to 3 decimal places, then, what we get here is 1.017 there. Okay? So that gives us the value of b to 3 decimal places. Now, what we also want here, then, is the value of a to the nearest integer. So for a part 2, then, well, all we're going to simply do here is use either equation 1 or equation 2, right? It really doesn't matter. You can use either equation here. So let's just use equation 1 here. So ab to the 20 is equal to 52. So what I know here then, using ab to the 20 is equal to 52, then I know here that a is equal to 52 over b to the 20, right? Where b is 1.017. So therefore then a here is equal to 52 all over b to the 20, which is 1.017 there. Like so. At this point here, just simply use a calculator, right? And then to the nearest integer here, what we get here then for a is 37. Okay? So there we have it then. That gives us the solution here to part A of this question. Now for the next part of this question, then part B, it says, with reference to the model, interpret the value of b. So we should have just about enough room then for part B. We'll probably have to clear the screen for part C, but we'll cross that bridge when we get to it. So for part B then, so for part 1 here, we want to interpret the value of b. So what does b represent here? So let's just go back to the model, right? So my model here is going to be 37 times by b, which is 1.017 to the power of t. Now b then, this value here is what we call the growth factor, or the factor by which the population increases each year. So b is the growth factor But you can also just say here then is the factor, or the factor by which the population grows each year. I'll just write this down in full here. By which the population grows each year. Okay. And there we have it then. So this is the solution here to B part 1. And then finally for B part 2 here, I'll just do that over here then. So for B part 2 then, we want to interpret the value of A. So what is A here? So A then is simply the population in 1970. So you can either give that as 37, I say that the population is 37 million in 1970, or just simply A is the population. So A is the population in 1970. Okay. And there we have it then. So hopefully nice and straightforward here in interpreting the value of B and A. That gives us the solution there to part B. And then finally to finish with here, we have part C. Now, there's a little bit of work involved here in part C. And as we can see then, we don't have much room on the screen, right? So let me just quickly pause the video, clear the screen, and then we can have a go at answering part C. So as we can see, then we've now cleared the screen here. So let's just have a go then at part C. Now what I've also included here is the value of A and the value of B as we determine those in part A here, because we do need those to help us answer part C. Now, what it says here then is using the model, find the year when the population is predicted to reach 100 million. So all we need to simply do here then is just replace P with 100, right? And then just solve for T. So nice and straightforward then. What we get here is 37 times 1.017 to the T is equal to 100. Okay, so first step here, divide both sides by 37 to get 1.017 to the T is equal to 100 over 37. Now for the next step here, I'm going to take logs of both sides, right, and apply the laws of logarithms here. So in that case, then what I get is T ln of 1.017 is equal to ln of this fraction here, so 100 over 37, like so. And in this case here, right, if we just want T, we just divide both sides by ln of 1.017, right? Nice and straightforward here. So therefore, T is equal to ln of this fraction here. So 100 over 37, all over then ln of 1.017. So just put this into your calculator, right? And what we get here then is 58.9811, so on and so on. So in that case then, we're looking for the year when the population is predicted to reach 100 million. So what I do here is round this up to the next integer, or the nearest integer, I should say. So don't forget here, and don't forget then, what we're looking for here is the year when the population is predicted to reach 100 million, right? So we want the year rather than just the value of T here. So what I do then is round this value of T here to the nearest integer. So T is equal to 59. And don't forget then, T here is the number of years after 1970. So 1970 plus 59. So 1970 plus 59 gives us 2029. And in that case then, to summarize here, the year when the model is predicted to reach 100 million is 2029. Okay. And there we have it then, right? So all things considered, pretty straightforward. Just be careful that you do give it as a year, as opposed to just the value of T, right? That's the only thing to be slightly careful of there. But there we have it then. So that gives the solution here to part C and the solution to question 12. Now for the next question here, question 13, this is split into two different parts. So part A then is just simply an application of integration by parts. And that should hopefully be accessible to most students here. However, part B then, we want to find the particular solution of this differential equation here. And that is certainly more challenging, right? But we'll cross that bridge when we get to it. So starting off then with part A here. So what we want to do here then is use integration by parts to find this integral here. Now what I've also included in the top right corner here is the relevant result then for integration by parts as it is given in your formula book. So what I've got here then is the integral of x cos 3x with respect to x here. Okay. Now to begin with then, what we need to do here is choose u and also v prime. So for u here, it makes sense to choose x, right? Because if I differentiate x, I simply get 1. So u here is equal to x. And as we've just mentioned here then, u prime is 1. What that means here then is v prime is the remaining function of cos 3x. So cos 3x there. We also need to integrate this here then with respect to x to obtain v. So nice and straightforward then. That is simply 1 over 3 sine 3x there. Yeah, perfect. Good stuff. I was struggling with some basic integration there, but there we go. Good stuff. So this integral here then, well, like we just said, right, just a simple application of integration by parts. We won't need to do it twice because u prime here is 1. So just need to use this result here. So in that case, then the integral here of x cos 3x with respect to x here is equal to, so it's uv, so that is x times 1 over 3 sine 3x. So x over 3 sine 3x minus then the integral here of v du by dx dx. So v, which is 1 over 3 sine 3x, times u prime, which is 1. So you get 1 over 3 here, sine 3x. And of course, we're integrating here with respect to x, right? So what I'm going to do here is use linearity and take the 1 over 3 outside the integral here. So, all right, the 1 over 3 here, like so. And let me just quickly erase that there. Perfect. So, obviously, we can't do anything with this here just yet. So I get x over 3 sine 3x. That's fine for now. So this integral here, what would that give us then? So this would give us minus cos 3x over 3, or minus 1 over 3 cos 3x, whichever way you prefer to write that. It's just the same thing. And don't forget here then that we times this by minus 1 over 3. So I've got minus 1 over 3 times by minus then 1 over 3 cos 3x. So if we simplify this here then, what do we get? We've got x over 3 sine 3x. I've got minus 1 over 3 times minus 1 over 3. So just be careful of the signs here, right? This would simplify to give us 1 over 9. We get 1 over 9 cos 3x. Okay? And because this integral here, right, has no limits, don't forget we do also need our constant of integration. So plus c there. Okay? And at this point here, that would be absolutely fine here and would suffice as a solution. What I am going to do, just because I think it looks a little bit neater here, is just write this over a common denominator. So if I do that here then, I would need to times this one here by 3 to get my denominator to be 9, right? So that would give me 3x. So 3x sine 3x plus cos 3x all over 9. I've got plus c here. Perfect. Good stuff. So there we have it then. That gives us the solution here to part A. So that is the result then for this integral here by parts. Now for the next part of this question, then part B, we now want to find the particular solution of this differential equation here, given these boundary conditions, right? We need to give our answer here then in this form. So y squared is equal to f of x. Now, what you should notice here straight away is this looks pretty similar to what I had then in part A, right? I've got x, y cubed cos 3x. So what I need to do here is separate the variables, okay? So what I'm going to do here then is divide both sides by y cubed. So on the left-hand side here, we get 1 over y cubed. And basically anything on the left-hand side here, we want in terms of y. So I get 1 over y cubed dy, like so. And this here then is equal to, so on the right-hand side here, we just want anything in terms of x. So I simply get then x cos 3x. Okay. Now, once we separate the variables like this, right, all we simply do here is just integrate both sides. So what I've got here then is the integral of 1 over y cubed dy is equal to the integral then of x cos 3x. Oops, I forgot the dx there as well. Don't forget that. Perfect. Okay. So this integral here was from part A, right? So that's going to be useful. And this integral here, well, just basic year 1 integration, right? Shouldn't be anything challenging there. So let's just evaluate each integral here as we go. So the integral of 1 over y cubed dy, that is simply, I get minus 1 over 2y squared there, like so. And this here then is equal to this integral, which gives us the following. So I get 3x sine 3x plus cos 3x all over 9 plus c. Okay. Now, at this point here, I need to use these boundary conditions. So we know that y is equal to 1. So y equals 1 when x equals pi. Okay. So simply, all we need to do here, right, is just substitute y equals 1 and x equals pi into this here. Okay, this equation here. So what do I get here then? So I get minus 1 over 2 lots of 1 squared. So that's just minus a half, right? So minus a half is equal to, so I get 3 pi. So 3 pi sine 3 pi. Like so, plus cos 3 pi. All over 9 plus c. Okay, and obviously what we want to do here then is just solve for c, right? So what do we get here then? So sine 3 pi is just 0. Cos 3 pi is minus 1. So this here is 0. This here is minus 1. So I get minus 1 over 9 plus c. Just make a note then. So minus 1 over 9 plus c is equal to minus 1 over 2. So just add 1 over 9 to both sides here. So therefore c is equal to minus 1 over 2 plus 1 over 9, which gives us minus 7 over 18 here. Okay. So where do we go from here? Well, let's just go back to this line here and replace c with minus 7 over 18. So what we get here then is, and let me just kind of box this off here just so it doesn't cause confusion, because I appreciate we're going to start going into our solution from part A. So just box off part A there. So, like I said, right, let's go back to this line here. So I've got minus 1 over 2y squared is equal to this here plus c. I get 3x sine 3x plus cos 3x all over 9. And then plus c here. So c is minus 7 over 18. Now, I've got a lot of fractions here. Things are looking a little bit messy. So what I'm going to do here then is just times through both sides here by minus 18. So times through by minus 18 on both sides of this equation here. Okay. So if we do that here, what do we get then? Well, on the left-hand side here, just be very, very careful, by the way. It's really, really easy to make a mistake with this question. There's a lot going on. And obviously, we've got a lot of negative signs thrown in here. So yeah, so just take your time with this question. Just be very, very careful. So minus 1 over 2y squared times by minus 18 here. So negative times a negative, it becomes positive. So I've got 18 over 2y squared here. So that's going to give me 9 over y squared here. So 9 over y squared. Perfect. What else do we have here? So times it through by minus 18 here. What I'm going to get then is minus 18 times by this here. So let's make a note here. Minus 18 times by this full fraction here. So I'm not really bothered about the numerator here. That's just some expression. But because I'm dividing by 9 here, this will cancel to minus 2. This just cancels to 1. So just times through the numerator here then by minus 2. So what I'm going to get here then is, so we get minus 6x sine 3x. So minus 6x sine 3x minus 2 cos 3x. Okay, so minus 2 cos 3x. I'm trying to be as careful as possible here that I don't make a mistake as well, because there is always a good chance that I do make a mistake. And I've got the minus 7 over 18 here, so I times by minus 18, that just gives me plus 7. Perfect. Up to now, looks good. Now, what I want here for my solution then is y squared is equal to f of x. So what I'm going to do here then is flip this, and obviously just flip this, right? This is over 1. So let's get y squared over 9. So y squared over 9 is equal to this here then over 1. Okay. So sorry, let me reword that. I've kind of lost where I'm up to. So I've got this here. That's over 1. So if I flip this, I also need to flip this. So this is now 1 over this here. There we go. We got it the right way around. So 1 over all of this here. I'll write the 7 at the beginning as well, just given that that's positive. So 7. I'll put that next as well. So minus 2 cos 3x. It doesn't really matter though. And then minus 6x. So minus 6x sine 3x. Perfect. We're nearly there, guys. So we just want y squared, right? Y squared is equal to f of x. So to finish with here, I've got y squared over 9. I just want y squared. So we just times both sides by 9 here. Now I've got y squared over 9. So if I times 3 by 9 here, the 9 just disappears. And then I'll also erase it here on this side. 1 times by 9 is just 9, right? I get y squared is equal to 9 all over 7 minus 2 cos 3x minus 6x sine 3x there. Perfect. There we go. So it's now in this form here. Y squared is equal to f of x. So hopefully my demonstration here of our particular solution does make sense. Like you can see, 4 marks here. This is quite a tricky question, but just 4 marks anyway. But hopefully the explanation and demonstration there did make sense. Okay, so there we have it then. So this here was the solution to part A. And this here then, in fact, the solution is that pretty. Let's kind of highlight it here. So y squared then is equal to, so you should get this here, right? So 9 over 7 minus 2 cos 3x minus 6x sine 3x there. Okay, and there we have it. Beautiful. Okay, so good stuff. If you got the solution, perfect, well done. If not, like I said, just go back, quickly rewatch it and see where you made the mistake. But there we have it. So it gives us the solution there to question 13. And then finally, to finish with here, we now have the very last question, question 14. So for the first part of this question and part A, we want to prove that for x between 0 and 1, arc cos x is equal to arc sine of the square root of x minus 1 here. So where do we even begin here with part A? Well, the first thing to do here is let y be equal to arc cos x. So arc cos x here, like so. And what I'm also going to do here is just make a quick note then. So we know here that x is between 0 and 1. So x is between 0 and 1. And what that means here for y then is y is between 0 and pi over 2. And this will become important a little bit later on. But for now, that's absolutely fine. So for the next step here, what I'm now going to do is take cosine of both sides of this equation here. So on the left-hand side, then what I get here, nice and straightforward, is simply cos y. And then on the right-hand side here, I get cosine of arc cos of x here, or cosine of arc cos. They're the inverse of each other, right? So they just cancel. I just get left with x here. So cos y is equal to x. And at this point here, we now need to use a trig identity to progress. So what I need here is sine squared x plus cos squared x is identical to 1. And what I want here then is sine squared y. So we want sine squared y here. So we can easily obtain that by just rearranging here. So we get 1 minus cos squared y. Like so. What I actually want here is just sine y. Okay. So sine y here, and let's just be slightly careful. So for sine y here, well, because y here is between 0 and pi over 2, what that means then is sine y must be greater than or equal to 0. So when I take the square root in just a moment here, we omit the negative solution. Okay, that's all that tells us here basically. So sine y then is equal to the square root here of 1 minus, now what I've got here is cos squared y, but cos y is equal to x. So cos squared y, well, just square both sides here. We get 1 minus x squared. Okay? Like I said before, we omit the negative solution here. And at this point here, we don't just want sine y, we actually just want y here. So if I've got sine y, I just want y. Let's take arc sine of both sides here. Okay, so arc sine of both sides here. And in that case, then what I get here is y is equal to arc sine. So arc sine of the square root here of 1 minus x squared. Okay, and then just linking this here and this here, it verifies this here. Okay, or it gives us our proof basically. So therefore then, y is equal to arc cos x, where y is arc sine of the square root of 1 minus x squared. Let's just write this down in full here. So arc cos x is equal to arc sine of the square root here of 1 minus x squared. Okay, exactly as we required. So as required there, bosh, some beautiful maths there. And it doesn't just stop there, right? We've got part B, part C, and part D. So let's just continue then. Now for part B then, what do we want to do here? So it says, give a reason why this result is not true for x between -1 and 0. So we could easily kind of disprove this result here by finding a counter example, right? Just using disproof by counter example. So for example then, if I let x here, so let x be equal to -1 over root 2, then arc cos x here, so arc cos x is equal to 3 pi over 4, and arc sine, so arc sine of the square root then of 1 minus x squared, when x is equal to -1 over square root of 2 here, that would give us pi over 6. Now, clearly then, 3 pi over 4 is not equal to pi over 6. So, in that case then, what we just say here is that arc cos x is not equal to arc sine, so arc sine of the square root then of 1 minus x squared for x between -1 and 0. Okay, and there we have it then. So this here is just a disproof by counterexample. So there we have it then. That gives us the solution to part B. Now for part C then, what does it say here? We'll do part C over here. So it says by expressing arc cos x in terms of y, show that arc sine x plus arc cos x is equal to pi over 2. And what we're given here then is that y is equal to arc sine x for x between -1 and 1. So what I've got here then is y is equal to arc sine x. Like so. So let's just use this hint here, right? So like it says here, by expressing arc cos x in terms of y. So let's take sine here of both sides. I get sine y is equal to x here. Okay. And at this point here, we now take arc cos of both sides. So what I'm going to get then is arc cos x. Let me just make a note here. So take arc cos of both sides, just so it's clear what I'm doing here. So, like we just said then, we get arc cos x is equal to arc cos of sine y. So arc cos of sine y, like so. Now, at this point here, we need to be quite clever with this and how we go about kind of getting to this point here. Okay. So what I'm going to do then is just use here. So I'm going to use here the fact that sine x here, in fact, given that it's sine y, right, in terms of y, so sine y is identical to cosine of pi over 2 minus y. Okay, we're going to use this relationship here. So in that case, then what I've got here is arc cos x is equal to arc cos of sine y. So just replacing sine y with this identity here. We've got arc, not arc sine, arc cos. There we go. Of cos of pi over 2 minus y, like so. And arc cos of cosine here, well, again, they're just the inverse of each other, so they just cancel. And in that case, then what I've got here is arc cos x is equal to pi over 2 minus y. So pi over 2 minus y there. Okay? Now, y here is arc sine x. So what I've got here then, let's go to the top, is arc cos x is equal to pi over 2 minus y, where, as we just mentioned, right, y is arc sine x. So pi over 2 minus arc sine x. So just add arc sine x to both sides here. And therefore then arc sine x plus arc cos x is equal to pi over 2 as required there. Okay, so there we have it. Like you can see, not the easiest, type of question here that we're working through, but hopefully my explanation and demonstration here does make sense. Okay, so there we have it then. That gives us the solution to part C. And then finally, to finish with here, we have part D. So, as we can kind of see here, we don't have much room. So let's just quickly clear the screen and have a go then at part D. So as we can see, then we've now cleared the screen here. So let's just have a go then at part D to finish with. So for part D then, it says, hence or otherwise show that the solution to this equation here can be given as follows. So for part D then, the fact that it says hence or otherwise would suggest to me anyway that the solution from part C here is probably going to be quite useful to help us answer part D. Now what I've got here then, let me just start by writing it down. So arc sine of x minus 1 is equal to 2 arc cos of x minus 1. Now, what I'm going to do here then is just use a substitution. So if we let y be equal to x minus 1, then what I obtain here is arc sine y is equal to 2 arc cos y. Like so there. Okay. And we know then, which isn't going to be the most useful given that I've just cleared the screen, but what I know here then is arc sine y. So arc sine y is equal to 2 lots then of pi over 2. So pi over 2 minus arc sine y here. Okay, just using this result here from the previous part of the question, right? Part C for arc cos y here. So arc cos y then is pi over 2 minus arc sine y here. Well, let's just times through by 2 here. So arc sine y. So 2 lots of pi over 2, that's just pi. And then get minus 2 lots of arc sine y. So minus 2 lots of arc sine y there. Okay. So let's just keep going here. So let's just add 2 arc sine y to both sides to get 3 arc sine y is equal to pi. Let's just divide through by 3, right? So arc sine y is equal to pi over 3. Now, I just want y here, right? So I'm going to take sine of both sides here, because we've got arc sine y on the left-hand side. So sine of both sides here. In that case, then, y here is equal to sine of pi over 3. And sine of pi over 3, then, well, in exact form here, I obtain that y is equal to root 3 over 2. Now y, don't forget here, we've used this substitution, so y then is x minus 1. So what I've got here is x minus 1 is equal to root 3 over 2. And then finally, x here is equal to root 3 over 2. So root 3 over 2 plus 1. And we want this here, right? So I want this here. So let's just get this over a common denominator here. In that case, then x here is equal to, it's going to be 2 plus root 3 over 2 there. Exactly as we require here. So again, as required there. What a beautiful question. Okay, so hopefully, you know, gave a good challenge there for the very last question. And there we have it then. So that gives us the solution to the very last part of the very last question, question 14. And that brings us to the end then of these video solutions here to this mock exam paper, predicted paper 2 or mock paper set C, paper 2. Bit of a tongue twister, but there we go. As always, if you did make it all the way to the very end, well done. Congratulations. These videos are always quite lengthy. I do appreciate each and every one of you that does watch these videos. So again, thank you so much for watching. And then finally, to finish with here before we end the video, I just wanted to say best of luck for the upcoming A-level maths exams. So again, as always, thank you so much for watching, and I'll see you in the next video.